Welcome everybody to my talk about Fractan. You probably will have never heard of Fractan before, so I'm just gonna dive right in. What you're looking at right now is a machine, a Fractan machine, which we'll use during this talk. So let me take some time to explain it. The most the number in the front is basically the state of this machine. And besides the state, there's a number of fractions. Mind you, the number at the end, the 55, is actually also a fraction, but the denominator, the number below the division bar is 1, so it comes out as a natural number. There's some buttons on top. The first button will reset the machine if we need to. The next button will make a micro step, and we'll go into that a little bit shortly. And the next step is to make a big step, or whatever that means. And then below the numbers, there is a list basically of numbers that have been the state. So this machine, which we're looking at now, is of particular interest. But let's see what happens when we do a micro step, basically. So what's going on now is that we are taking the first fraction on the list, 17 divided by 91, and we try to multiply it with the state and see if we get an integer, a whole number. And this isn't the case. The calculation that is made here is for our convenience. In fact, you could do it in your head, but why use your head when you can have a computer? So if that doesn't work out, if it's not an integer, we go on to the next fraction. So the next fraction, we're going to try to multiply it with the state and see if there's an integer out. And we go through the list a number of times until eventually there is an integer. So the foremost last fraction, if we multiply 2 with 15 divided by 2, out comes 15. So this will be our new state. So basically what this machine does is it has a state, a number in front, and we're going to try to multiply that in each step with each fraction, and we'll take the next step will be the first integer result. So to reiterate, we're going to take the first fraction, we'll take a look at will the product of the state and the fraction we're currently investigating form an integer, and if that's not the case, we're going to go to the next integer all down the line, and because the last fraction is an integer itself, we'll make sure there will always be a next state. So the product of these numbers, of the first fraction that will give an integer number, that will be our next state. So we could do this because we are told to look at this screen and make progress. And in order to do this but it's faster, we're going to disregard the intermediate results and just go straight to the next state. And you will see this list grow, and there will be a sequence of numbers appearing, which isn't all that interesting until we get to 4. So why is 4 important? Well, it's a power of 2. So it's a number that's only made up of multiplying 2 a number of times in itself. And I'm giving you time for this lecture, or actually this talk, to figure out what these numbers are precisely. Because if you take a long time, and this will take a lot of button presses, eventually another number, another power of a 2 will occur, but you have to wait a long time for it. So there's the next power of 2. And my question to you is, and I hope to explain this in this talk, is, well, why are these numbers occurring and why are these powers of 2 are important? So having set the stage of this strange machine, I'm going to explain to you what this machine actually is. So this machine is invented by John Horton Conway, which you probably know, at least from his work on life. So life is a cellular automata. Makes cool pictures, and it's very interesting. And there is a biography written in which he expresses that he hates his curation life because he has done all these interesting mathematics and nobody knows that. But life, the one thing that he basically is tired of now is the one he's famous for. So unfortunately for him, that's why he's famous. But to honor his wish, we're going to look at Fractan instead of life. So the reason why you want to look at Fractan is not because you're going to write your next killer app in it, not because it's particularly useful or easy to program in it, but nonetheless, you can learn things. And this book, The Pragmatic Programmer, is a book that I received when I started working, and my first employer, everybody who started at the place got this book, and I like books. I read it vigorously, and one of the tips this book has, because it's a book full of tips, which is basically invest regularly in your knowledge portfolio, which isn't very catchy, so you don't very often hear this. But what you maybe have heard of is one of the sub goals of this tip is to learn a language each year. So why would you want to learn a new language? Again, it's not to beef up your curriculum vitae, your CV. It's not because you want to look smart. It's because learning things broadens your horizon. It will teach you new things. It will give you a new vantage point to solve problems. Just like having a conference like we're having now is a meeting place of like-minded people, which you can exchange ideas and pick up new ones. So although Fractan isn't a language that you're going to use to write your next killer app in, it can teach you a lot of things, and it teach you how to solve certain kinds of problems, which might end up being useful in your day-to-day job. But again, it's also fun and interesting to learn. So let's look at Fractan a bit more. So one of the important things of Fractan is the state, and that state is resembled into a number. So this is just a random number I picked. It's my personal favorite, basically, but I'll not go into that. And what you can do with this number, which will help the understanding of Fractan programs, is decompose it in its prime dividers. So if you would do that, and you take out your calculator and you type in 3 times 5 times 229, you'll get the original number, 3,435, out. And this isn't a unique number. You can do it with any number. Let's do it for 60. If you decompose 60, you'll get 2 times 2 times 3 times 5, which will be 60. And these numbers that I picked, those aren't random numbers. Those are very specific numbers because these numbers are all prime numbers. So what are prime numbers? Prime numbers are numbers that are only divisible by itself and 1. So all the numbers in this list, and this list is very big, are only divisible by 1 and by the number itself. So for example, the reason that 4 isn't a prime number is that 4 has a divisor 2, which is different from itself. So one way to create these prime numbers, besides looking them up on Wikipedia, is you can start with a grid of numbers. For example, if you want to know all the prime numbers below or equal to 60, you would write them down like this. And then the first thing that you do is you stripe off 1. So 1 isn't a prime number. And the reason for that is that one of the properties that you would like these numbers to have is that if you decompose a number, then basically what you want is that there's a unique way of decomposing the number, and if in prime numbers. And if you would allow 1 to be a prime number, because 1 is allowed to be multiplied with any number, so you can have different kinds of compositions if you allow 1 to be a prime number. So we don't want that. We want to have a unique factorization. So 1 isn't a prime number. So that takes care of 1. And then basically the rule is, with this grid of numbers, is that the first number you haven't visited yet will be a prime number. So 2 in this instance is a prime number. And what you can do is reason about, well, the multiples of 2 can't be a prime number anymore because they will have a divisor, because that's what the multiple is, of 2, which is different from the number itself. So what you can then do is cross all the multiples of 2 and remove them. Those aren't prime numbers, for sure. And then again, like I said, the first number on that list that hasn't been visited, in this case 3, will be a prime number. So 3 is a prime number. We can do the same trick. We can look at all the multiples. For sure, these will not be prime numbers, so we can take them off the list. And we have the first unvisited number 5 in this case is again a prime number. So we take the multiples, strike them out, look at the next number, look at the multiples of that, strike them out, and then we have a number which is interesting in the sense that the only multiples of 11 that are able to be on this list have multiples that are starting from 11, because all the smaller multiples are already crossed off this list. But if you do the math and you take the time and you do 11 times 11, which will be the smallest multiple of 11 that should be on this list, or should be striped off of this list, 11 times 11 is 121, which is bigger than 60. So the multiples of this number, or any number bigger than that, can't be on this list we're looking at right now. So we know for a fact that all the remaining numbers are all prime numbers. So this process is very famous. It's called of the sieve of Eratosthenes, which was a Greek that thought about prime numbers a lot and came up with this this form of generating them. So that's a nice way of having a list of prime numbers that we're going to use apparently later on, because like I said, prime numbers are used to represent numbers. And one concern that you could have with this method is that, well, if I have a huge list and cross off all the multiples, eventually all the numbers will be crossed off and there will be no primes anymore. Luckily for us and for Fractan programmers that you all going to be, this can't happen. There's a famous theorem in mathematics. It's called the infinitude of the primes. And basically what it says is there are an infinite number of primes. And this is also a very old theorem. It's attributed to Euclid, which did a lot of things with geometry. And his proof basically goes like this. Let's say we have a charlatan saying that he has a finite list of all the primes. Let's call them P1, P2, up until Pk. For example, somebody claims that all the primes are just 2, 3, and 5. Well, we can think hard and come up with a number that will have prime numbers, because all numbers have prime divisors, which isn't on the list. So one way to do that will be to multiply all these numbers together. So we multiply P1 times P2 times Pk, and we add 1. So for our example, that will be we multiply 2 times 3, which is 6, multiplied with 5, which ends up with 30, and we add 1, 31. So if we reason hard about this number, there can be two cases. One case will be that this number in itself is a prime number. Well, that will be a new prime number, which isn't on the list because it's bigger than each prime number on the list that is given, because at least one is added to them, but I think they're a lot bigger. Or this number, if it's not a prime number, will have divisors. And one of these divisors will have a prime factor, which is different from the number of the list, because each prime factor on the known list leaves a remainder of 1. If you divide the number 31 with one of our prime numbers, you'll have a remainder of 1. And that remainder will make sure that there will be a number, a prime divisor, that is different from the known primes. In our case, 31 is a prime number, which you can have been seen on the previous slide, but this isn't always the case. So luckily for us, and I say luckily because this is basically one of the interesting aspects of a Fractan program or a Fractan machine, is that there are an infinite number of primes, which is very interesting. We'll get back to that soon. So this list of numbers, these lists of prime numbers, they're infinite, and we saw that you can take a number, you can decompose it into the prime factors uniquely. In this case, that will be 2 to the power of 2 times 3 times 5. Or in other words, if you take that list and you multiply and you register the number of times a prime factor occurs in a number, you get this list. So there are 2 factors of 2 in the prime decomposition of 60. There's 1 prime factor of 3 in the prime decomposition. There's 1 factor of 5 in the prime decomposition. And for all the other prime numbers, there are zeros. This is a way of looking at a number. A number is just a word which could potentially be infinitely long, or at least unbounded, and you set the exponents here. Because we are working with exponents, another way of looking at this is that if you have the value of the exponents indexed by the primes, this is just a different way. And that's basically is the first insight about Fractan. Fractan basically operates on a bank of registers. Those registers hold non-numpative numbers, so 0, 1, 2, 3, and upwards. And each register is indexed by a prime number. So if you go back one step, the index of the 2 is the prime number 2, which basically says the number that we're looking at has 2 factors of the prime 2. And again, there's 1 factor 3, and if there's 1 factor 5, and 0 factor 7, 0 factor 11, that will show up there. And because the state is a number, at each moment in time, there are only a finite number of non-zero registers. Again, if you look at this number, the tail of the prime numbers all have register value 0. So that's our first insight. Basically, a number is not just a number. It's an infinite bank of registers where only a finite number of values are non-zero. So that's a great insight. And this fact alone is already very important because it allows you to encode a lot of information in a single number. And basically, if you are philosophical and would share a moment with me in the bar at a later time when we're allowed to come close to each other again, we can philosophize that a computer basically is just manipulating a huge number. Like if you take the entire memory of a machine, that's a humongous number, and all the computer does is manipulate that number in some sort of sense. So maybe you haven't thought about it like this, but Fractan programs makes this clearly obvious that there is a way to encode a lot of information in just a single number. And if you think hard about it, a computer already tells that. So there were 2 kinds of numbers. There was the states, and there were the instructions, the fractions in the Fractan program. So let's look at a Fractan instruction, which is basically a fraction. So this is a fraction, and we've just learned a trick of decomposing numbers so that we'll learn something more. And because this decomposition is important, we're going to do this for a fraction as well. So 14 apparently, or not apparently, is 2 times 7, and 15 is 3 times 5. So this is a fraction. And this is very typical for fractions because if you would have a common number in both the numerator, the thing above the division bar, and the same number below, because you can eliminate those, you will have a reduced fraction. So it can be the case that there's a prime number occurring in both the numerator and the denominator. So that's one rule. And more importantly, because we're going to take a look at the division algorithm for fractions, is for a specific prime, if the number of prime factors in the top part is less than the number in the bottom part, in the denominator, then by successively striking the same factors, you will end up with a reduced fraction where there's no prime number in the numerator, the top part, and there's the difference of the number of prime numbers in the lower part of the denominator. Well, you can turn this around. If there are more prime factors of a certain kind in the top, then you will reduce that and you have an integer. So this is a criteria for when a fraction multiplied with a number will be a fraction again. It has to have at least as many prime factors in the numerator as the number itself. Because if they are the same and you take a fraction and you basically tick them off, you will end up with a 1. So the next and second insight of a Fractan program basically is each instruction, each fraction of a Fractan program operates on the bank of registers in the following way. The denominator, the lower part of the fraction, subtracts the number of primes from the register, and the numerator, the top part, will add to the corresponding prime factors in the representation. So this is all a bit of hand waving and I think it's time to look at certain examples. And we'll do that now. So we see here one of the simplest Fractan programs in itself. The state is exposed as a number of fractions, just like the fractions are, so that we can see what happens when we multiply things. And what we basically see here is that there's only one fraction, a half, and the state is a number, is a power of 2. So because powers of 2 have the attribute that it's divisible by 2, and you'll see that the second insight is, well, if we have a factor in the denominator, it will subtract the number of occurrences of that prime from the register that we have in this bank. So this is a prime number, and the next state will be 2 to the power of 4. And if you keep dividing, if you keep executing, stepping this machine, you will end up with the number 1, which we have foresaw. And basically what you see here is that the state will decrease the number of 2's in its expression. So this is the simplest machine. Basically what it does, it zeroes out a register. If we equate the numbers with registers, then the register value at index 2 will become 0 because of this machine. It's a nice machine. It's simple because it's only one fraction, but already with this simple machine, if we slightly modify, we can do something interesting. So the next machine of this type will be doing the following thing. So the denominator is still 2, and you know what happens with that. It will reduce the number of the value of the 2 register, and at the same time, it's multiplying with 3. So the second part of the second insight is that it will increase the register value of 3. So making that clear with the expression. So the 2 to the power of 5 times 3 over 2 is an integer, because the number of 2's in the exponent is bigger or equal than the number of 2's in the denominator. But at the same time, we're going to add a 3 to the state. So the next state will be 2 to the power of 4 times 3. And if you do this again, well, you've seen this from the zeroing out factor, is that the exponent of 2 will decrease and the exponent of 3 will increase at each step. So if we step through this, what you will see is that the sum of those exponents of 2 and 3 add up to 5. And if there are no more exponents of 2 available in the state, we're finished, and we end up with a copy of the register value. So we started with the register value in the register 2, and we end up with a register value of the same value in register 3. So this basically is moving a register value. And the terminology of the last 2 machines that I used mimic the instructions that typical CPUs do on registers. So already maybe you can see where this is heading. We can express certain fundamental operations by picking the right fractions. Well, let's do something interesting with this insight. So this is a slightly more complicated machine. It has not 1 but 2 fractions, but we have learned from the previous examples what these fractions do. So the fraction 5 over 2 in itself will move the value stored in the register 2 to the value to the register 5. So it will move 3 units from 2 to 5. And similarly, the fraction 5 over 3 will move the value of register 3 over to the value of register 5. So basically, if you think hard about this, you will come to know that this will create an addition of these numbers. And we can look at this. So again, the first fraction will create the next number, and it will have reduced the register value of 2, and it will have increased the register value of 5. This will happen up until that there's no more 2 in the state. So the first fraction doesn't give you a whole number, an integer number, So it will have to look at the next fraction, which, because there still are factors of 3 in the state, will be a number, and it will add 1 to the register value of 5. So if you step through that, it will diminish the register value of 3, having added it to the register value of 5. And what we end up is with a machine that will add 2 values in registers and put them in another one. So this basically is a machine that can do addition. And already this is a very advanced concept. Not only can we increment, but we can also do addition with this framework of a language and machine. Let's look at another example. Instead of a sole prime number, there's a fraction that has 3 factors of 2 in the denominator, and the state is also a power of 2. So I'll give you some time to venture a guess what this machine will do. I will obviously go into it, but basically what this will do is it will decrement by 3 the exponent of the register 2, and then it will stop if that isn't possible. So basically it's testing whether or not a number, 7 in this example, is divisible by 3. And that isn't the case. And if it would be the case, we would end up with 1. And if we are a bit more secure, we can basically do division. So the first fraction we've seen this already, for every multiple of 3 that is available in 8, we'll add to the register value 3. And then, if that's the case, so we've seen this before, then there's something left over, and what's left over will be put into register 2. So basically what we've done now is we have started with the number 8, and we've asked the question, how many times goes 3 into 8, which basically what fraction is 4 to 8 divided by 3, and what is left over. So this is divider with remainder. So there's one thing that I didn't talk about, which I'm going to talk about now, and that is copying a register. And what you could try to do is something like this. Well, I know that this fraction, 3 over 2, will will move the register, and if I add another number, it will increase a temporary register, the temporary register 5. And then what I could try to do is when this fraction doesn't work anymore, I could try to move over the other fraction back. But if you look at that, as soon as the state doesn't have a factor of 2 anymore, the first fraction can't work, the next fraction will work, it will put back a fraction of 2, but then there's a problem, because now the first fraction can work. And this will muck up your grand scheme of things, and will not make a copy of things. So one way to remedy that is to use a sentinel value. So instead of the state that we just had, a pure power of 2, we added a sentinel, 7, and we also used that in our numerator. So now when we divide, as long as the sentinel is there, we can make the same computation basically, and put another sentinel 11 there. So that will be the new state. And now, because there's no sentinel 7 anymore, the first fraction doesn't work anymore. So that's not an option. And this fraction, the 7 over 11, will put back the 7 that we need to perform the first operation. And this can go a long way until all the fractions of 2 are gone. And then, because the sentinel 7 is gone, but it's replaced with the sentinel 11, the next fraction to work will be the operation that replaces 2 with 5s. And this step will eventually copy back the original value. So we started with a value in register 2 and a sentinel. You can ignore that one basically. And we ended up with a state that has the original value and a copy of it. So this is basically copying a value, which you're going to need. And that's basically the last insight that I'm going to talk about. You can use sentinels to turn on and off certain kind of computation. And with these insights and a bit of working out, you can come to a program construction. So what I'm going to do is I'm going to switch over to a blank canvas and walk you through the computation of doing multiplication, which is a bit harder. So to set the stage, what I try to achieve is if I have a register 2 with a certain value A and a register 3 with a certain value B, I want to end up with a certain value in register 5, namely the product of A and B. So for example, if we have 2 to the power of 2 and 3 to the power of 3, what I would like to end up with is 5 to the power of 6, 2 times 3. Okay. So we've had some experience with these machines, and I'm going to create a symbolic notation for that. It's basically a dot is sort of an instruction. And what I want to do is if the state is divisible by a half, I want to transition in another state. So this doesn't really make sense in the terms of Fractan programs, but we'll get there eventually. And if I have one factor of 2 available, then I want to add the number of B to the register 5. So one way to do that, we already learned that, is to divide by the number of 3's and add to the number 5. So this is a fraction that will move over the value in register 3 to the register value 5. But we need, if there are more 2's available, we need to be having an original copy back. So we're going to use a temporary value 7 to make an actual copy. So this is the copy machine that you just saw. So if that doesn't work anymore, and this is the double arrow, we want to go to another screen, because basically what we now want to do is we just moved the value of the register 3 to the registers 5 and 7, but we want to have the original situation back, that we have the same value back in 3. So this is just moving again, and this moves the value of register 7 by dividing it over to the register 3. And this is basically the move machine that you see. And if that's finished, if that doesn't finish anymore, you have to go back to the original machine. So this is a pictorial representation of a machine that will do addition. But how do we go from this pictorial representation to an actual list of fractions that will do this? Well, there's a few intermediate steps. One of the intermediate steps is that we make actual nodes for each of the nodes that are present in our pictorial representation. And we're going to write them big because we're going to label them with numbers in a moment. And one thing that I don't really like is these loops. So for each loop, you're going to break them apart in 2 steps, like this. And then we're going to just basically copy over the information. So this is copying all the information that we've just made. This is the fraction that we're looking for. And we basically always want to go back. So this is just a fraction of 1 over 1. This will always make an integer number regardless of this. And this arrow basically means do this with a lower priority. And finishing this image, we'll have made it like this. We eliminate the loops, and we have to go back like this. So if you look at this diagram, it doesn't have labels for the nodes, and these labels that are going to be the sentinels that we talked about. And if we have a list handy of our numbers, prime numbers, we see that it will start with 2, 3, 5, 7, 11, 13, 17, 19, and 23. But the numbers that are already used in the fractions, we can't use them because they have meaning in our algorithm. So the numbers below the line are usable, and we can use them to label the nodes. So this is a label, gets labeled 11, 13, 17, and 19, and 23. So now we have a dressed up diagram, but again, we could use another description of this diagram by just listing what happens with each label. So for the label 11, basically if we encounter a fraction half, we go to the node with label 13. Basically, this is what this arrow means. If you're in node 11, go over to node 13 when it's divisible by half. And if you would do that for the entire number of fractions, you will end up with a list like this. 17, and mark you, there is a transition of lower priority, that always happens when the first priority doesn't work, to go to 19. And here you can see a glimpse of the future, because 13 and 17 are basically pairs that toggle, should I move the register value of 3 over to 5 or 7 or not by stencils. And we'll get back to that later. So for 17, we always transition to 13. And then there are 2 labels left. For label 19, we're going to write down if it is divisible by or multipliable by, we go to 23. Otherwise, with a low priority, we go to state 11. And 23 will always go to 19. So this is a different description of the same diagram, basically. But then again, these aren't fractions. And the reason of the method, how you come to a fractional list, is like this. So basically, these are sentinel values that will help you to transition to all these computations, basically. So you'll take the fraction that you're interested in, and then you divide by the line number. So divide by 11, and you multiply it to the target, which is 13 in this case. And that's your first fraction. And the next fraction, we can do another example, is 5 times 7 divided by 3. And we have to multiply with the 13 of the label and multiply the numerator with the target. And this variant is of lower priority. So we're first going to do the pair of loops that correspond to a loop in our diagram. So the next is we're going to write down the same similar thing is we are going to 13 and we came from 17. And here you can see the work of a sentinel. So 13 is a sentinel for this computation. And we exchange it with another sentinel called 17. And as long as that works, we're going to put them back. And otherwise, we're going to do the lower priority one. And we're going to divide by 13 and go on to the next computation. That's basically how you read these things. And if you work out the last part, I will do it a bit quick. And then you will get the following fractions with a higher priority of 23, and then basically going over to the final computation. And if you do, this is the list of fractions that corresponds to our earlier algorithms, of writing down the multiplications. So we could take a look at how that worked out. We have a number, and we're interested in multiplying 2 and 3, and we've stored that in the state with the sentinel to get things started. And you will see first that it will divide by 11 and add a new sentinel, so it will copying over it to the state of 5. And if you do this, you will end up with a long list of numbers, and I'll skip to the end, where, well, this is a sentinel value, but where the value of 5, which is 6, is indeed the product of 2 and 3. So thinking back of the first Fractan machine you've probably seen, at least in this talk, it corresponds to this machine. And basically, this is a diagram that, if you would study hard, will show you that it does a long division of a number of tries, and basically it finds prime numbers. So this machine will give you all the prime numbers as power of 2. So each time you have a power of 2, the exponent is a prime number. So basically, this is a prime producing machine. And this is the sole reason, basically, that Fractan programs exist. So what are the takeaways? So one of the takeaways is, again, you basically are now a Fractan programmer, and I will set up a page so that you can try out to program a Fractan program later on. I'll put that in the Slack. But that's not the real thing that I want you to take away. The takeaway that I'm interested in is that this strange and esoteric programming language of Fractan has taught you that you can represent a fairly large amount of information in just a single number. That's one thing. But more importantly, by learning new things and engaging with people with different backgrounds and different views, you will broaden your horizon and will make you basically a better person. I hope you enjoyed the talk. If there's any questions, I'll be on Slack. Next week, there'll be a Q&A if you're interested. And I will make sure and we'll put it on the Slack to create a page that allows you to program these Fractan programs and to play with this language yourself. So thank you for your time and hope to see you soon. If there aren't any questions, I could tell you why I got interested in Fractan. So I'm an avid reader and I'm a mathematician by trade. So I read a lot of mathematics books, and there was this book I read that had this prime producing machine, and I got curious. So how does this work? How do you make sense of what is happening here? So I delve into that. So my personal motivation was I want to understand these things, and that is what basically I think drives me is I would like to understand things and pick things apart and then make sense of it. And then enjoy basically.
I guess any coding produce such language.
So you would use this language because it's so specific. But what you could use it for is, like, for example, if you were making a respirator and having to interface with hardware, a lot of software still operates on the level of the bits, and by introducing a domain-specific language, basically, that will translate the things that you want to do, like pump out oxygen now, and translating that into something that a computer can understand. That's how another thing that you could take away.
Yes, I can just point that it's Church encoding for prime numbers, and Gödel in his theorem, he uses this encoding.
Yes.
Yes. So yes, it's nice.
Dan.
Yes.
Okay. Do you have any experience with Agda?
I do have experience, a little bit of experience with Agda. I've looked more into Idris, which is also a dependency type language.
And any thoughts about it? It's too. It's also exotic, quite exotic.
Yeah. So the interesting thing of dependency type languages is that you can express things in your type system that allow you to reason about your program on a higher level. So like already Scala is a far more expressive language than its parent Java. And this allows you to very precisely express what your intentions are. And adding type-dependent languages, it even more allows you to express a certain kind of inspiration. And this is, I think that our industry has a modeling problem in the sense that a lot of programmers, the only types they want to use are the basic types like integers and strings. Like everything is a string, everything is a number, and that removes you from this allows you to reason about your program in a sense. And having type-dependent languages or a language like Scala, which has a rich type system, allows you to express concepts far better than just sticking to the basics. Does that answer your question?
Yes, it is, but also it is complicated.
Yes.
It's precise, but it's complicated. It's hard to find a real-world problem worth to be solved with Idris or Agda or whatever. It's too tiny scope, so that might be a reason.
I do think that it is complex, but I think that the complexity is inherent in our business. Like solving real problems is hard, and I do think that although Iris and Agda are languages that are on the fringes of academic research, which Scala maybe is as well, it does offer you a trade-off, because instead of implicitly in code writing down what your assumptions are, you can make them explicit in your types. But again, it's a trade-off. I agree.
It's trade-off for time to market, but it takes a lot of safety to you, because you can prove your business logic, and you can prove in compiled time that it is safe. So
yes.
it's not just a trade-off, it's also a strong part, but not so much real world business problems requires it.
That's true. I totally agree.
Thank you.
Thank you.
Great talk.
Thank you.
How you come to Fractal?
That's a good question. So I study mathematics at university. So I have I like that, and I like reading about mathematics and doing it. And I have several books actually that mention Fractal, and it's so bizarre if you first come upon it. These set of fractions are so otherworldly and produce interesting things, especially the prime numbers, that I was motivated to really get to know what makes these programs tick. Well, having an understanding of that programs for me is a way to get a grip of things. And I also really like to share knowledge, especially of these esoteric languages, and that's why I came to know Fractal.
And what do you develop usually in real life?
Yeah, so I'm not using Fractal for that, and I don't hope anybody has to do that for GitHub. So at my day job, we're mostly using Java, and my team and I are looking into Kotlin as a programming language. So we're a big company. We're a power company. So there are also teams that do forecasting of energy usage, which mainly use Python or R. I'm not really much involved with that, but sometimes questions come up, and I do lend a hand. And we have various applications that, with a front end that we write in Vue.js. So it's a regular stack, not that much Scala, unfortunately, but it's interesting though.
For Scala, you plan to adopt Scala, yes, or just looking?
So I think that Scala is a very interesting language that has a lot of nice features and allows you to express things in certainly in types, which is great. But I do think that it has a steep learning curve that allows you to do a lot of things in a lot of different ways. And for a team to work on a Scala project and have a uniform style of writing Scala is very hard. I have never seen a team do that very well, especially because we are a very big company with a lot of different developers with a lot of different backgrounds. So I don't think that that we anytime soon will be using Scala in our company.
Mm-hmm.
So no. So probably not.
Mm-hmm. So it's just because learning curve. Interesting. Mm-hmm.
Well, so one of the things that that you need to keep in mind is that not everybody knows Scala at a company, and if you want to invest time in writing Scala, I think you also need to invest time into learning Scala well. And I'm not sure if a lot of people are interested in doing that. So, for example, if you compare that to Kotlin, Kotlin is very well adapted if you know Java. So if you know Java, you can probably pick up Kotlin within a week. You probably don't write idiomatic Java Kotlin from the start, but the mainstream is just it's almost Java, but with a nicer syntax. Whereas with Scala, there's some language features that are so far remote from the Java world that you just that's very much harder than to adopt Kotlin, I guess.
Mm-hmm. Yes, it's interesting. I am here. Another thing that Scala was used to select such kind of people. and to have a good tea, good tea on. So maybe the idea of selecting the language is the idea of selecting that type of people, and maybe the language which you doing in spare time, it is a good criteria.
Yes, yeah, and it's a very nice language, a very nice feature, and it does show you what is capable in programming languages. But because it's a hybrid language with so many ways to do something, I do think that having a consistent style with your teams is very hard to maintain.
I have a question. What do you think about Dotty? What's your impression?
So, because I don't write Scala for my day-to-day job, I haven't looked into Dotty just yet. I saw a few talks on the conference, and it seems a nice improvement. But I have no experience with it for myself, so I couldn't really react on that.
Okay, thank you.
I have a question about Fractan.
Yeah.
As far as I can tell, it's Turing-Complete, right?
That's correct, yes.
So, do you know if there could be a hardware implementation of it, and if it would be sufficiently efficient, or that's completely idiotic idea?
So it's definitely an interesting question. So in general, Fractan programs are very slow. They need a lot of states to achieve things. So from the get-go, I wouldn't recommend doing that. But considering the fact that you need to represent arbitrary fractions as your states, and they tend to grow quickly, the numerator and the denominator. So that would mean that you would have a multi-length word to accurately represent your state. I do think that it is possible in a limited way, so you can run probably all programs, but it is possible to create hardware to run a Fractan program. But I wouldn't recommend it. It would be a nice exercise in thinking about, well, what should I achieve doing that? But I don't see any benefit other than having a laugh and doing interesting, funny stuff. But I don't think the next computer architecture should be based on this machine. No.
Yes, thanks. Another question. Prime number sieve, it's nice, but one would like to sort of do a map and get the logarithm to have the actual prime number. So how do you think it could be possible to implement such a map to the actual prime number?
So it depends on what you think of a map. Like the first Fractan program I showed is, in a sense, a program that produces primes. So you could adopt it to accept also a number, and then it will give you the nth prime, for example. But that is a bit cheating, because it has to go through all the prime numbers and then give you the next one. So I'm not aware that there is, and I don't think that it is possible to give you the nth prime number without also listing the other ones. So I don't think that there is a map that could do that, but I would have to look up some research to be sure.
Because as it's universal language, in principle, you could implement on top of it. First, for example, like bytecode interpreter.
Yes.
And then above it, why not, for example, implement the Scala language, and then do maps and whatever, and get your prime number sieve in a clean way.
Yes.
again,
That's possible. But I do think that there are, so like, but I think that on the fundamental level that there isn't a function or a map that will, if you input 37, will output the 37 prime number. But I could be mistaken there. So, but of course you could introduce the hierarchy of languages on top of a Fractan machine and do it in that way.
okay, thanks.
What will be the big idea for other computing, maybe? What you think about this?
Yeah, so if I look at programming language nowadays, and I'm not that old, but a few years back, they're all very much text-based. And of course, there's the language like Scratch, which allow you to move blocks around and stuff. But they were all very much on the syntax of individual characters, or at least words. And often enough, when I reason about programming, that's not the level of detail that I'm reasoning about. I'm reasoning about concepts and how they relate to each other and how they need to change. So I think that the next step in programming would be to have some sort of interface in which allows you to express your ideas in a much more natural way than of typing out the individual characters. I do also think that it's a long time before that will be a thing. But then again, maybe I'm mistaken. Like a few years back when AlphaGo has beaten the world foremost Go player, I was shocked. Like that was promised to me that will be far into the future, and there it was. There was this program that could play at an insane level, far beyond the human level, play Go. So maybe it's just around the corner, but at least I think that
deep learning interface, yes, it's quite interesting. Yes,
yeah, it is. So I think that will be benefit a lot of people, like expressing your ideas without going down through writing characters. But I do think that's a long way off.
Okay, thanks.
Thank you.
Thank you very much. Nice to see you.
Nice to have you.
Thank you.